Okay, I hope I'm audible. So, hello and welcome back to the weekly uh, discussions on wheel mobile robots. I'm Isaac John. So, this is actually a special session, apart from our weekly sessions, which was usually scheduled on Tuesdays. This is actually a special session on a Saturday. So, the purpose of this session is to briefly cover, all the topics that we have covered until so far. So up to until previous Tuesdays, we have actually covered, we have actually covered a summary of all the topics that we have covered until week 7, and we have also solved some, sample tutorial questions, which are very similar to the questions that you can expect in the weekly quizzes. So yeah, so just to top it off, we have actually covered all the topics up to week 7. From kinematics, then dynamics, then we have also seen topics regarding perception, navigation, and localization. So before our final session on the coming Tuesday, we will briefly have a very rough or a very brief rough overview of all the topics that we have covered till week 7. So yeah, we'll start with week 1. So I hope I'm audible. If I'm not audible or if there are any issues, please let me know through the chat. My internet could be a bit dodgy, it could be a bit unstable. So if I'm not very clear, you can let me know through using your microphone or through the chat box. So yeah, without further delay, we would just get on with a brief review of all the topics, starting from week 1. So in week 1, what the topics that we covered was, we actually gave a very brief introduction to mobile robots and manipulators. So like typically, robotic systems can be classified as mobile robots or manipulators based on their, mechanical architecture. And based on the end action or their end effect on the environment, you can basically classify them as either manipulators or mobile robots, right? So the main objective or the main feature of a manipulator is that it basically manipulates the objects around it. So like if you have an object in your workspace, the robot manipulator would, probably manipulate an object, which means it can pick an object up. It can, change its position or its orientation, or it can do some task with an object and place it elsewhere. But that would be the effect of a manipulator on the environment. But in case of a mobile robot, any effect on the environment would result in the motion of the motion of that robotic system itself, right? So the only effect a mobile robot can have is through its it's if it is through its wheels in case of a wheel mobile robot, or through its legs in case of a legged robot, or it could also be in form of a thrust, if you're talking about a drone or an aerial mobile robot. So the effect on the environment causes the motion of the robotic system itself, then such mechanisms can be classified as mobile robots. Then once we have seen that, we have actually furthered, we have actually furthered classification of mobile robots based on the based on the type of locomotion we are employing, right? So like for example, in case of a mobile robot, various types of locomotions are possible. The robot can locomote through through legs, and within the legs itself, there are plenty of plenty of other configurations, and it can have two legs like a human being. We call them as biped robots. It could have four legs. like a robot dog. Quadrupeds, we call them as quadrupeds. It can have 6 legs. We could call them, hexapods. Which somewhat moves, which somewhat realizes its motion based on the coordinated movement of all the 6 legs. Uh, yeah. Then apart from legs, it can move through. What other types of locomotive systems are available? We have wheels. We have uh, aerial robots. Then we have tracked robots. The military vehicles. They have this sort of tracks. Which is very useful for outdoor locomotions. Then you even have underwater mobile robots. So these are the various locomotion strategies that can be employed in a wheel mobile robots. And then we furthered our investigations on mobile robots, right? So within mobile robots, we have to further narrow it down to locomotion using wheels alone, because that is the purpose of our course. We are mostly focused on wheel mobile robots. Then to finish off the topics on week one, we have actually seen what is meant by this the term called degree of maneuverability. So in order to get to this degree of maneuverability, we have to go through some other degree of some other degree terms. We have seen them to be degree of freedom. We have actually seen the definition of what a degree of freedom is. Then some other degree terms that we have seen of over the duration of week one was degree of mobility. Then we have actually seen one more term called degree of steerability. And finally, all of these definitions would lead to the term called degree of maneuverability. So whatever we define using degree of maneuverability, this is actually a very key point we should be aware of when we move on to week two, right? In week two, we have actually seen various, developing kinematic models for various kinds of mobile robots, various kinds of wheel mobile robots, using different wheels, different kinds of wheels, using different configurations. And the main distinctive feature, or the way you can classify, all of them, all of the types that we have considered, we have to use, you can actually distinguish them, or you can actually characterize them based on their degree of maneuverability. So like we'll discuss more on that when we go on to week two. But for now, we'll just briefly go through some of the key terms that we have encountered on week one. So I don't want to read all of them out loud, because we have actually reviewed all of these in the weekly lectures. We have basically seen the definition of the word called effector, because this is the first thing that the first definition that we have actually seen, or we have actually studied in this course. So basically, effector is any robot or robotic device that has an effect on the environment. So that means the effect can be, the the manipulation of the objects, or the effect can be, the motion of the robot itself. So like based on the type of effector, you can actually classify a robotic system as manipulators, or locomotion systems, or locomotive devices. So like we have also seen the definition of manipulators and locomotion systems. And we have also seen the key differences between manipulators and mobile robots. So in this course, we are mostly focused on mobile robots, that too on wheeled mobile robots. So this is the topic of interest, or topic of discussion for our course. But then, just to just to have a very clear idea of, the distinction between the manipulators and wheel mobile robots, we'll simply go through a few key points. So the main distinction is, the manipulators operate on a constrained workspace. Because as you know, in case of a manipulator, the base or the first link of a manipulator is always fixed to the ground, right? So in that regard, if you know the motion of each and every link, you can actually have a very good estimate of the entire workspace. So the entire workspace is very well defined. It's fully determined in case of a mobile robot. Whereas in case of a mobile robot, due to the fact that it can move around in its environment, and if you consider, the area in which it can move to be infinite, it can basically have an unconstrained workspace, right? If you deploy a mobile robot in a house, it can basically move anywhere in the house. So the workspace becomes, anywhere in the house. And if you deploy that same robot in a different house, its workspace changes. Or if you deploy mobile robot outdoors, maybe for military search and rescue operations, the workspace is practically unbounded. It can basically go anywhere it wants, and all the communications can be done through through long range radios, or things like that. So in that regard, workspace is one of the key characteristic that that basically uh, helps us distinguish between manipulators and mobile robots. And then another thing is, how they measure positions of each and every point within that system itself. So in case of a robotic manipulator, it's not that difficult to estimate the position of each and every points of that robot itself, right? Because as you know, a robotic manipulator will be having, actuated joints at every joint, at every possible joints. So each of these joints, they have an encoder inbuilt in it within the joints. So like based on that encoder reading, you can actually plug those values into a kinematic model, and as a result, you can estimate the coordinates of each and every point uh, of that mobile robot, right? You don't need any other external sensing. But in case of a mobile robot, you actually need external sensing to determine its own position, right? Because in case of a mobile robot, it has an it has an unconstrained workspace. So the main challenge of a mobile robot is to identify its own position within the workspace, right? So for that, it has to sense its surroundings. Like for example, if my eyes are suddenly closed, and if I am picked up from my bedroom to my living room, I may not be exactly aware of where exactly I am on my living room, right? I need some sort of visual references or some tactile references to know where I am on my living room. So like if I open my eyes, based on the distance between the walls or maybe some furniture, I can understand my position within that living room. So that same sort of thing, a mobile robot will also require, it has to use its external sensors. It can be a vision sensor, or it can be an ultrasound sensor, or it can be a proximity sensor. It has to use some sort of an external sensor to determine its own position within that environment. So there is a need of external sensing in case of a mobile robot to locate itself in the environment. And in case of the third point is, it may or may not need to perceive the outside world around them. So, in case of a robotic manipulator, it may or may not require. So, depending on the application, it may or may not require additional sensors to perceive the world around them. Because in case of a manipulator, they are always they mostly work on a well-defined constrained workspace. And if there are obstacles within the workspace, which it has to avoid, uh, then the motion of that obstacles, or the how these obstacles are, they are all very well defined within its workspace. Like, and most probably in case of an industrial robot, the obstacles are most probably going to be static. Their positions, their trajectories are always going to be well defined at all times. Or if the robot has to move, or if the manipulator has to work around a dynamic obstacles, their state at each and every point is actually very well defined. So most probably it may not really require any external sensing to avoid obstacles. Or if there are dynamic obstacles, it may require. So depending on the use case, it may or may not require to perceive the outside environment. But in case of a mobile robot, it surely needs. Certainly, it should require, or it requires external sensing to avoid obstacles, because as per a mobile robot, everything within the environment is it's highly dynamic, and the behavior of the obstacles cannot be premeditated or predefined. So like if you deploy a robot in a house, maybe a vacuum cleaner robot, people keep on moving around it, so it has to adapt within its environment. And the way it adapts is using its external sensors. And the final point is constrained workspace. Like this is what we have discussed in the first point. So workspace, it's a redundant point. So yeah, those are the key characteristics that helps us distinguish between a manipulator and the mobile robot. Yeah, moving on to mobile robots. So here uh, we still haven't narrowed it down to. I hope I'm still audible. If there are any connection issues, please let me know. So on the next slide, we move on to the basic introduction to mobile robots. So we are still in mobile robots. We haven't narrowed it down to real mobile robots. So in case of a mobile robot, let's see what defines a mobile robot, right? So there are a few points. A mobile robot is an automatic machine capable of locomotion. Locomotion is the process by which uh, you know the effect on the robot on the environment causes the motion of the robot itself. And what we have seen earlier, it's not fixed to a location. It can roll, walk, fly, or swim. Any modes of movement or any modes of locomotion is possible as per the definition of a mobile robot. And they are typically less structured in their operation and are likely to use more sensors than robotic manipulators. Like as I have said, they are deployed onto a workspace with very minimal knowledge about their surroundings, the obstacles that they are dealing with. So most probably they'll only probably know their starting position and their end position. So everything in between, the environment, the obstacles, and how to reach from the start position to the end position, everything is pretty much unknown to the mobile robot. So it has to learn, as it moves around the environment, it has to learn, it has to learn to understand, or it has to learn to perceive the environment around it. And at the same time, it also has to plan a path from its current position all the way to the final goal position. So because of all this learning involved, that typically they are less structured, unlike a robotic manipulator. Because in case of a robotic manipulator, every little detail within its environment is actually well defined, and it's pretty much fed into the control algorithms of a mobile robot. So it does not really have to be self-aware, as self-aware as a mobile robot. And there are key fundamental questions or challenges a mobile robot should address. So which can be briefly which can be briefly classified as, answering these three questions. So the mobile robot has to answer to this question, where am I, or where its current location is. So for that, it has to make measurements and, take measurements and model the environment, using its own sensors. It has to, perceive its environment, and at the same time, it also has to create a map, of the environment. And then, where am I going? So it has to answer the second question. So once it has made, or once it has taken a set of measurements about its environment, right? So like I'll just depict it as a map. Once the robot, if you consider this point to be the start point, and at the diagonally opposite end to be the goal position, and at the beginning, the robot will be measuring, and it'll be able to, identify some obstacles within the environment. And, it'll basically have a partial map of the whole environment. So once it does that, it has to, localize itself within the environment. So like once it has created a map or a partial map, it should also identify its own position within that map it just created. So that process is what we call as localization. So in week 5, we have actually seen two different schemes of localization. One is called Markov-based localization, and the other method is called Kalman filter localization. We have actually seen that in detail in the lectures as well as during the weekly tutorials. So that's about the second point. It has to identify itself within the map it just created. And then how do I get there? It has to plan a path to its goal and control its motion. So like once it has created a path, it has to navigate around the obstacles, and then eventually it'll have to reach, it'll have to find an optimal path to reach its goal position. Right? It can have multiple such options, and it can go through this way, it can go through this way, it can go through this way. So multiple such paths are available, and the key thing is that based on the topics that we have seen on week 6, the robot will have to, once a graph or a math has been constructed, it has to select an ideal path or a most efficient path using some graph search algorithm. So based on a graph search algorithm, it will basically select an ideal path. So like once an ideal path has been selected, using the kinematic model and the dynamic model, and using the motion control, the motion control will appropriately take will appropriately give some control inputs into the actuator so that that selected path can be realized. And then moving on to the next slide, we also discuss about what are the various subsystems that makes up a mobile robot. So these are the various subsystems. The primary subsystem is actually locomotion. The mode of locomotion that a mobile robot would use. Whether it is wheels, legs, maybe some aerial mode of locomotion, etc. And then the kinds of sensors that a mobile robot requires. Based on it can be actually classified depending on the type of sensors that we are using. In week 4 we have seen two different classifications of sensors. Whether it is measuring something internal to a robot, such as the reading of the encoders or the battery levels, things like that, or the inclination of the robot chassis. All these things are internal to the robot. We call those sensors as proprioceptive sensors. And if the sensor is measuring something external to the environment, such as probably the distance to the obstacle or the distance to the nearest obstacle, or if it is capturing something using some camera sensors, they can be classified as exteroceptive sensors. And depending on whether or not they, they require or they need some power source for their actuation, you can again classify them as active sensors, or if it does not require any power, you classify them as passive sensors. And the third subsystem is actually reasoning, which deals with how the robot maps the measurements to its actions. So the whole chapter about perception basically tells you about that, how you can use the meaningful informations from the sensors and then translate them into control inputs. So our topics on week 5 about localization basically tells in detail about how a robot reasons itself. And then on week 6 we have actually seen the design of various motion controllers, and we have seen some more further classifications on motion controller, whether it is an open loop controller or a closed loop controller, whether it is a kinematic controller or dynamic, whether it also takes the dynamics of a robot into consideration. All these classifications we have seen in on week 7, mostly dedicated to uh, motion controllers or design of motion controllers. And on week 8, we'll have actually see a very brief overview regarding the communication strategies uh, that is typically employed in mobile robots. How an operator can communicate with mobile robot, or if you have a system of or a cluster of mobile robots, how can they communicate among each other? So like we'll discuss that on week 8 tutorial sessions. And the key issues that we have to address on locomotion is the stability of the entire system, right? And that basically depends on number of contact points, center of gravity, static and dynamic stabilization, inclination of terrain. So like as far as we are concerned, the stability of a wheel mobile robot is pretty much not really concerned, right? Because all these things, center of gravity, static and dynamic stabilization, they are more relevant to a legged robot, especially a robot, especially if it is a bipedal robot with just 2 legs, right? So like if a robot is standing on 2 legs, you can actually see how unstable that it is, right? A small disturbance can knock it out of its stable equilibrium, and it can actually fall over unless it has some mechanism to stabilize itself. But in case of a wheel robot, especially with three or more wheels, you can actually see it's actually very stable. If you try to knock it off, it won't easily topple over, right? So because of that, there is some level of inherent stability for wheel mobile robots. And there is also this point of contact points. It can probably make some difference in wheel mobile robots, because it's very similar to how unstable a table or a chair can be. If there is a if one of the legs is actually smaller, or if there is a level difference in the floor, right? Because if any one of these is a factor, you can actually observe that the table will always wobble, right? So at a point only three legs will be in contact. And the reason is that if in order to fully define a plane, you need only 3 points, right? Or to define a line, you need only 2 points. To define a plane, you only need 3 points. So in case if there is a level difference, or if there is a length difference of each of these legs, only 3 points will be in contact, and the fourth point, depending on where the entire weight is concentrated, the table can wobble. So the same thing can also happen with mobile robots with more than 3 legs, right? Wheel mobile robot with 3 legs. So like if there is a level difference, only three legs will be in contact at an instant. The fourth wheel could be, floating floating somewhere, so whatever force it tries to exert on the ground, it won't, because it will be floating above the ground. So to avoid such things, you probably need some suspension, or some pushing force that ensures that the wheels will always be in contact with the ground. So you can ensure that using using suspensions for wheel mobile robot. But again, that is not really a concern for us in this course. And then contact characteristics, the area of contact, angle of contact, friction, all these things are key issues that has to be addressed in locomotion. And then the type of environment, whether the environment is, an engineered surface, whether it is indoors, whether it is smooth, or whether it is outdoors, rugged, maybe it has a lot of undulations, we have to consider those things uh, into the design of a mobile robot. And then we have also seen the type of land-based robots. It can be a wheeled mobile robot. You can actually have a tracked robot. You can have a legged robot. You can have a hybrid robot. So in this example, what you see is actually a hybrid robot, right? It has legs, four legs like a quadruped. So basically, it can have very high flexibility of movement, like any quadruped. Like, so, for example, if it has steps or obstacles, it can use its legs, to overcome those obstacles, right? And you can also see that there are wheels at the end of each of these legs. So like when it actually operates within a very smooth surface, it can extend all its legs, and it can move through just using wheels. So hybrid locomotion is a very efficient and effective method of localization. If you feel that the robot will have to encounter extremely smooth engineered surfaces, as well as other surfaces with lots of obstacles and undulations. And then we have actually defined uh, our study of kinematics, what we actually study using kinematics. So we then get on to the mechanics part of the course. So the first three lectures deals with the mechanics of wheel mobile robots. So basically, mechanics of robotic system consists of two topics. The first topic is called kinematics, and the second important topic is called dynamics. So in case of kinematics, we only study the motion without considering the forces that causes the motion, right? So we all know that in order to cause a motion, or in order to cause a change in motion, there has to be some sort of an external effort, or forces or moments that has to act on a body. So in kinematics, we don't consider the forces. We study only the motions. How the motions are transformed from one body to another, to the other body, or how a motion is transferred from all the four wheels into the chassis of the robot. All these things we consider through kinematics. And then we actually later defined some terms that start with this degree of freedom, degree of mobility. So the first thing is degree of freedom. The first degree term that we discuss is something called degree of freedom. So it basically means the minimum number of variables required to describe a system, right? How many variables do you require to describe the position and orientation of a mobile robot? So one example is that if you have a coordinate system like this, X and Y, and you have a mobile robot like this, so you can consider this mobile robot to be a rigid body. So the key advantage of consider considering it as a rigid body is that you can represent this entire rigid body, or you can represent the positions and orientation of each and every point within this rigid body using a coordinate frame, that is attached to that rigid body. So I'll call this coordinate frame attached to the rigid body as the coordinate frame B, X, B, Y, B, right? So if you know the position and orientation of this coordinate frame with respect to a ground fixed coordinate frame, then you can basically fully determine the position and orientation of each and every point, right? If you know the location, if you know the position and orientation of this coordinate frame, each and every other point is always fixed, right, with respect to the body fixed frame of reference. So to determine the position and orientation of the body fixed frame, you need three coordinates, which are, the first two coordinates are position coordinates. Now, this distance, you can consider it to be the y coordinate, and this distance, you can consider it to be the x coordinate, right? So if you consider this to be the origin of the body fixed frame of reference, you need two coordinates, x and y coordinates, to locate the origin of the body fixed frame of reference. And you need one angular parameter. So I label that angular parameter as psi, right, to determine the orientation of this frame of reference with respect to the ground fixed frame of reference. So you actually require three x, y, and psi, three coordinates to fully describe the position and orientation of the body fixed frame of reference. So that is indeed true for any mobile robots, right? All mobile robots operate on a plane, right? Everything operates on a ground. So irrespective of the kind of mobile robot that you are using, you still require 3 degrees of freedom, to fully describe its position and orientation. So this is applicable for all land-based mobile robots and water surface vehicles. Water surface vehicles will not go underwater. It'll only remain in the surface of the water. But for aerial and underwater robots, you require 6 coordinates to fully describe its position and orientation, right? Because if a robot is moving in the aerial medium, or air as the medium, you require 3 position coordinates, right? You require 3 position coordinates, x, y, and z, and you also require 3 orientation coordinates for the orientation about x, orientation about y axis, and orientation about z axis. So in total, you require 3 position coordinates and 3 orientation coordinates. So in total, you require 6 degree of freedom for aerial as well as underwater modes. So that is the first degree term that we have actually defined in this course. We call it as the degree of freedom. Right. And then we discuss on the topic of frame assignments of, we discuss on, sorry, I hope my screen is visible. Yeah. And then we move on to the frame assignments uh, on a wheel mobile robot. So typically, as I was saying earlier, we require 3 coordinates to fully define the configuration of a mobile robot. So if I consider this big coordinate frame as the inertial coordinate frame, or the ground fixed frame of reference, I'll call this coordinate frame as xi and yi. And you have a mobile robot like this, like so, at any arbitrary orientation, and I attach a frame of reference like this on the robot, xb and YB. And I'll call this relative orientation between XB and XI axis as psi, right? This is how you assign the frame for a mobile robot, right? So one coordinate frame is attached to the mobile robot and another coordinate frame is attached to the ground. And then, you define the velocity along the XB axis as U. You also define the velocity along YB axis as V, and you define the angular velocity, or the rotation about the vertical axis or the Z axis about the robot's fixed frame to be R. Right? So if I call the velocity along the body fixed frame of reference as UVR, so these are the velocities with respect to the body fixed frame of reference. And the reason is that we always specify the velocities in body fixed frame of reference because the actuators are always mounted on the robot itself. So it's very easy to map. It's easy to determine the velocity of the motors or the control velocities if if the velocity of the entire robot is specified with respect to the body fixed frame of reference. But then you also often find a need to transform these velocities from the body fixed frame of reference to the inertial frame of reference. Right? You can do so by using this transformation matrix eta dot as a Jacobian matrix J of psi multiplied by zeta, where this eta dot I can call this as x dot y dot psi dot. These are the velocities with respect to the inertial frame of reference. And this Jacobian matrix can be, composed by this arrangement cos psi minus sin psi, cos psi, and 0, 0, 1. Then this multiplied by U, V, and R. And the reason for this mapping is, as an observer, we are always, our position is always with respect to the inertial frame, right? Because we are not sitting on the mobile robot. Our frame of reference should be always referred with respect to the inertial frame of reference, right? Because we are actually staying on the ground. And for us to visualize the motion of the mobile robot, it's always better to express, the coordinates of its positions, velocities with respect to the inertial frame of reference. So eta dot is actually for our benefit, and zeta dot is actually for the robot's benefit. To ease of transformation of velocities from the robot's frame of reference to the actuators. And these vectors, these vectors can also be easily derived. These columns. The first column is actually the direction cosines. This xb vector makes with xi, yi, and zi. And the second column is nothing but the direction cosines. This yb vector makes with respect to xi, y, and zi. And similarly, this 0, 0, 1 is nothing but the direction cosines. The ZB axis makes with respect to xi, yi, and zi. So that can be easily derived using very basic vector algebra. So yeah, that's about the frame assignments. Yeah, and we have actually pretty much talked about this relation. This is the fundamental relation that we deal in robot kinematics. So like when we discuss about robot kinematics, this is the relation that we have to recall, right? Eta dot as J of psi multiplied by zeta. And many a times you probably need, to switch back and forth between, each of these coordinates. So if zeta is given, in order to find eta dot, you pre-multiply zeta with this Jacobian matrix. Or if eta dot is given and zeta is to be found out, you pre-multiply eta dot with the inverse of the Jacobian matrix. So either ways, you can use this relation. And then in on mobile robot kinematics, we cover two fundamental problems, which is called the forward differential kinematics. This is just what we have talked about. So if theta is given, finding out eta dot is basically the forward kinematics problem. Or in case of the other way, if eta dot is given, finding out theta is basically the inverse kinematics problem. And these can be the first problem. Forward kinematic is similar to simulating or analyzing the mobile robot in velocity level, right? So if you consider this theta to be the input to the robot, finding out eta is, it's similar to how we perceive the robot or how we perceive the robot's reaction to this input. So it's like simulating a robot in velocity level. But on the other way, if this is how we want the robot to move, which is defined by this eta dot vector, what should be the control input that we should be giving? So that's defined by this problem, right? For any desired movement, what should be the control input? Zeta. So, that problem or this inverse kinematic problem is equivalent to, controlling the robot at velocity levels. And, the final topics of week 1 was something called maneuverability. We actually see the definitions of maneuverability, degree of mobility, and degree of steerability. So, degree of maneuverability is nothing but the sum of degree of mobility and degree of steerability. And degree of mobility is nothing but the degree of freedom the mobile robot manipulates directly through its wheels. So one example is that if you have a mobile robot like this, and if it has 4 wheels, right, and each of these 4 wheels are powered wheels. These 4 wheels are directly attached to motors, their own independent motors. And if you are independently powering each of these motors, their degree of mobility becomes 1 for each of these fields. So in total, you can actually sum up all the degrees of freedom, so that the total degree of mobility would be 4, because each wheel would contribute to 1 degree of mobility. And degree of steerability is nothing but the degree of freedom that a mobile robot indirectly manipulates by changing its steering configuration. So in this example, we have only considered each of these wheels to be directly driven, right? They are fixed wheels. They are not steerable. But in case of a tricycle like a configuration, very similar to our auto rickshaws. So there could be 2 passive wheels at the front, right? These wheels are neither powered nor steered. They are not powered or steered for a tricycle-like configuration. But there could be a wheel at the front, right? The front wheel could be steerable. You can actually have an independent steering axis. So you can use one independent motor for steering that front wheel, and for for the rotary motion or for the rotating motion of that wheel, you can use one more motor, right? So in that case, this wheel is also powered. The front wheel is powered and it's also steerable. So in that regard, that the front wheel will contribute to 1 degree of steerability and 1 degree of mobility. So in total, if you sum up the degree of mobility and steerability, the total maneuverability will become 2. Yeah, so that's about steerability, right? If it has if it has independent steering, through a separate motor, you add a degree of steerability by 1. And if a motor is directly attached for the rotary motion of that wheel, you can add the degree of mobility as 1 as well. And then in the later slides, we also talk about various kinds of wheels, that we employ on mobile robots. So I hope my slides are still visible. Should be some connection issues, I presume. Let me check. All right. Okay, so in the later part of the course, we have also considered different kinds of wheels. So until now, we have talked about conventional wheels, right? And the main assumption of a conventional wheel is that if you consider this to be the longitudinal section of a wheel, and these are the wheel hubs. While modeling a conventional wheel, we assume infinite resistance along the lateral direction. Infinite resistance along the lateral direction. So this is a fairly straightforward assumption that we can really have, because as you know, hold on 1 second. So yeah, as we know, a conventional wheel for a conventional wheel, it can only roll along the longitudinal direction, back and forth. It's very difficult for it to move sideways, right? Because of the grip a tire offers. It cannot slide in the lateral direction. And, because of that, that basically restricts a lot of mobility of a mobile robot, right? Just like how, if you have an automobile or if you have a car, maybe a regular four-wheel car, right? It can move forward and backward easily, and it can also rotate with some finite turning radius. But at the same time, it cannot slide sideways, right? It cannot really slide sideways because of the infinite resistance uh, that each of these conventional wheels provide. Or even they cannot even rotate about their own axis. So let me try to do something about this latency issue regarding the internet. I hope my screen is still visible. Let me check. Second. Is my screen visible? Can someone confirm that for me? Uh, hold on 1 second. Yeah, sorry about that. Yeah, so as I was saying, there were, in case of a conventional wheel mobile robot, with the conventional wheels, like so, they are unable to slide back and forth, like so, because they provide very high resistance along the lateral direction. But if you are using the wheels that you see over to your left and right hand side, they are sort of an unconventional wheel. They have these passive rollers, attached to their periphery. So that essentially enables them. Sorry for this connection issues. Yeah, so that essentially enables them to slide sideways. So if you are employing wheels like so, with these passive rollers, so these wheels can actually roll, about their hub axis, and at the same time they can also slide, back and forth, side to side. So that gives them additional capability to for a very high level of mobility. So let's see a typical problem that you can actually encounter in the weekly quizzes from the topics of week one. The question is for indoor applications with engineered smooth flows, which mode of locomotion is most efficient? Right. So this is pretty much straightforward, right? Out of all the examples considered, wheel robot is actually very efficient. If the surface is very smooth, right? Because legged robot, if you consider a legged robot, each of these legs will have multiple motors, right? For each of the joints of a leg. So and also you have a problem of stabilizing the robot, with the legs. So it brings up additional complexity. So in that regard, legged robot is not very stable and efficient for indoor applications. And tracked robot is also not very efficient for indoor applications because the track is very likely to slip, on a smooth environment. It won't be able to grip for the necessary traction. And hybrid robots, again, they can be used, but if the robot is exclusively used indoors, there is no use for legs. It will only increase the complexity. So again, the best possible option for locomotion is actually the wheel locomotion. And then moving on to wheel two, we are actually building up of what we have seen on week one. So we basically build a generalized wheel model for various different classes or various different kinds of mobile robot bases. And then we see how we can classify a mobile robot based on whether or not they are holonomic or non-holonomic robots. And then we have actually seen a few examples regarding how to use this generalized wheel model. Like we'll basically uh, you know have a rough overview. I don't want to go through all these derivations in detail because we have actually seen them in detail in the live discussions and in the lectures. So the key point or the key summary of this process is that this you can consider this to be the body fixed frame of reference, right? So if you know the velocity of the body fixed frame of reference to be u, v, and r, and if you consider this to be a wheel, a wheel with probably rollers, with where the passive rollers is defined by their their angle of orientation, you can actually map the velocity UVR to the angular velocity of this wheel. So if you consider this wheel to be the ith wheel, wheel I, and if you want to map UVR to the angular velocity of the ith wheel, you can actually use this generalized wheel kinematic model. Because ultimately, if you know the velocity of the robot chassis, using UVR, you want to know, what input you should be able to, or what input you should be supplying onto the wheels, so that you can achieve this UVR, right? You specify the desired motion using UVR, and to achieve this UVR, what should be the omega I, or the velocity you should be supplying into the actuator. So you can actually use this expression to derive, or to have that mapping between UVR and omega I. Right? And there are some parameters where AI is actually the radius of the wheel, and phi I is basically the angle this passive roller makes with this YCI axis, and theta bi is basically the steering angle. If the wheel is in one location like this, and if in another orientation it is like this, if it is a steerable wheel, or if it has some sort of an orientation with respect to this YB axis, that parameter is considered using this theta bi. And this dyi and dxi is nothing but the position coordinates of the center of this wheel with respect to this body fixed frame of reference. So this distance is dyi, and this distance, right, is dxi. So those are the key parameters that is involved in the mapping between UVR and omega I. And based on the different kinds of robot, you can have the mapping. The mapping will basically essentially change, right? So in case of a differential wheel robot, so this is the very simple case where you only have two powered wheels on either side of the robot, and this is how that mapping wheel configuration matrix would look like for a differential robot. And the only two parameters involved are the radius of the wheel, which is given by this term called A, and the distance between the centers of the two wheels, which is defined by this parameter called D, right? And in case of a four-wheeled skid steering robot, this is how that mapping looks like from UVR to all the four wheel velocities, omega 1, omega 2, omega 3, and omega 4, where, this is velocity of this wheel is omega 1, velocity of this wheel is omega 2, velocity of this wheel is omega 3, and velocity of this wheel is omega 4. And another case that we have considered is the case with four mechanism wheels, which has passive rollers, and for the first wheel, the passive rollers are aligned in this direction. And same for the third wheel, they are aligned in this direction. And for the second and fourth wheels, they are aligned in this directions. And then there are some parameters, because this phi I is actually always going to be fixed. So for wheels 1 and 3, phi 1 and phi 3 are 45 degrees. And theta B1 all the way to theta B4 are zeros. Right? Because, these wheels are not oriented, does not have any orientation coordinates with respect to XBI and YBI, right? They are aligned parallel with respect to XBI and YBI. So the parameters involved are this depth parameter called D, which is the distance between the centers of the wheels at the left side and the right side, and this parameter called L, which is the center to center distance between the front and the back wheels. And A is nothing but the radius of the wheels. So for a 4 mechanism wheel drive, the wheel configuration matrix would look something like this. And there is also one more configuration called a 3 omni wheel drive. And in this case, the wheel configuration matrix would look something like this. W, where A again is nothing but the radius of the wheel, and L is the radial distance of each of these 3 wheels, from the centroid of the robot chassis. Yeah, and now we'll solve a sample question. So as you know, the mapping between the velocity of the body fixed frame of reference, theta, to the vector of angular velocities is facilitated by a wheel configuration matrix called W. So depending on the configuration that you are working on, this W can be, it can be a non-square matrix. It can be a square matrix. And W can also be a non-square matrix. Right? And if W is a square matrix, it's actually pretty easy to take its inverse, because inverse for a square matrix is actually very well defined. But if W is a non-square matrix, if you have to take an inverse, right, as given in the question, because in the question, it is given as A is a matrix like so. So this is a 3x2 matrix, which has 3 columns and 2 rows. So what will be the Moore-Penrose pseudo-inverse of matrix A, right? Because in case of a non-square matrix, we have something called a Moore-Penrose pseudo-inverse. And depending on whether the number of rows is higher or number of columns is higher, there are 2 different kinds of Moore-Penrose pseudo-inverse, right? So in case in this given example, the number of rows is greater than number of columns, right? And if that is the case, you take something called a left pseudo inverse, which is given by this expression, A transpose A, the whole inverse A transpose. So if I call this as A pseudo inverse, so the left pseudo inverse of A is defined as, or rather, I'll just write it out here. Left pseudo inverse of A is defined as A transpose A, the whole inverse A transpose. So if you do that, you will get the pseudo inverse of A, which turns out to be option A, right? So this is only applicable if the number of rows is greater than number of columns. But if it were the other way, if the number of columns was greater than number of rows, you have to take something called a right pseudo inverse, which is something somewhat different to this expression. And I would recommend you to visit the lectures of Professor Shantakumar, or visit week 2 live tutorial sessions to see how these pseudo inverse metrics are derived, or how we arrived on this expression. It's not that difficult, but it requires some linear algebra manipulations, to arrive at this expression. All right, so those are the typical questions that we face with week 1. And then moving on to the summary of week 3, we now move on to mobile robot dynamics. So, dynamics gives you the governing equations of a mobile robot. So if you supply a trajectory into a mobile robot, so if you consider this to be a mobile robot, and you want the mobile robot to move use through a desired trajectory, you can define a trajectory using the position coordinates, velocity, and acceleration as a function of time. Then what should be the forces, that, or what should be the forces that you should be giving as inputs to the actuators, right? The control inputs that you should be supplying. So all these aspects would be covered in uh, uh, would be taken care of by the equations of motion or the governing equations, which gives you an idea about how, what is the state of a mobile robot at each and every instance of time. So for that, to derive this governing equations, you need to know, what are the forces that are acting on a wheel mobile robot, and how these forces, interact with the mobile robot to cause, the motion or the change of state of the mobile robot. So the main challenge is actually to derive the equations of motion of a mobile robot. So we have seen, two different schemes to derive the equations of motion of a mobile robot. So the two schemes we have considered are, the first one is using this Euler-Lagrange method, and the second approach is the Newton-Euler method. So both of these approaches would give you the same net final result, which is the equation of motion. So a general form of an equation of motion can be written as tau as d of theta, theta dot plus n of theta, n of theta, where this vector called tau is the vector of control inputs, which basically consists of the forces, the net forces along x direction, the net forces along the y direction, and the net moment about the z axis. And this matrix D is the inertia matrix. And this theta dot is nothing but the accelerations along, along the UV and R direction. And this n vector is called the vector of centrifugal and Coriolis effects. And you can actually derive the equations of motion using any of these two approaches, right? Euler-Lagrange or Newton-Euler methods. And we have also seen some key definitions regarding each of these terms. What do you mean by dynamics, and how dynamics, what dynamics aims to solve in from the context of a robotic system, right? And what is the purpose of deriving an equation of motion? How is it beneficial for us? You can actually use it for design, analysis, and control, of the system. Right? Design and analysis, like if you want to know, the forces acting on the members of the mobile robot, you can actually do proper design. You can make the design to be safe, right? Because otherwise, if the forces are more than what is allowed by the material, it could probably fail. So to to safely design a mobile robot, you need to estimate what are the forces that are involved. And apart from that, you also need to derive this equation of motion for facilitating or designing an appropriate controller for a robotic system. Right? And we talked about equations of motion. And similar to kinematics, there are two different problems in dynamics, which is called forward dynamics problem, and the second we call it as the inverse dynamics problem. Uh, and very similar definitions for forward and inverse dynamics, right? Analogous to the kinematics. So in case of forward dynamics, it says for a given input vector tau, calculating the resulting motion of the robot, eta dot and eta double dot, right? So one example is that if you have a mobile robot like so, and if you're supplying some forces to the wheels, maybe I'll call them as tau 1 and tau 2, how would the mobile robot move? Right? So it's like observing the mobile robot or, analyzing the mobile robot for a given pair of inputs, just observing how it would react to an input. And in case of an inverse dynamics problem, it's actually the opposite. For a given desired trajectory, find the required input vector. For example, if you have a desired trajectory, right, defined by position, velocities, and accelerations, and in order for the robot to execute this trajectory, what should be the control inputs that we have to give? So that is very similar to, it is equivalent to controlling the mobile robot to follow that desired trajectory. So that problem is inverse dynamics. Yeah, and then we have actually seen how to fully derive these equations of motion. And if you would like to know, you can refer back to uh, the lectures, or if you want to know a very concise uh, derivation for this final equations of motion, you can refer to that week 3 live discussion tutorial that was already shared. So there I was discussing, the derivation, the full derivation on the dynamic model. And one important aspect was that often at times you find it necessary to, have a change of coordinate or to define the dynamic equations of motion with respect to the inertial frame of reference, right? Because earlier, what we have defined earlier was something like this: tau as d of theta dot plus n of theta. So this entire equations of motion was derived with respect to the body fixed frame of reference. But sometimes in case if you ever need to, find an equivalent equations of motion with respect to the inertial frame of reference, something like tau of eta as t of eta multiplied by eta double dot plus n of eta dot. If you ever require to find out these equations of motion, or if you want to transform these equations of motion into the second equation with respect to the inertial frame of reference, you have to, do some following transformation of this D matrix and, N matrix to get this D of eta and N of eta. Right? So that sort of transformation can be made possible by using these expressions, right? Where D of eta is given by J Jacobian multiplied by the inertial matrix in body fixed frame of reference and the transpose of the Jacobian. So it's J D J transpose, and N of eta is nothing but minus J D J inverse J dot plus J of N. So you have to do that for obtaining the Coriolis matrix, or sorry, the Coriolis vector with respect to the inertial frame of reference. And how to derive these expressions were also discussed on week 3 tutorial sessions. And just like what we have seen in the with in kinematics, we also need to map the forces, acting on the body fixed frame of reference into the forces or the torques that is acting on the wheels, right? If F1 and F2 are the forces acting on the wheels, F1 and F2, and if Fx, Fi, and Mz are the forces acting on xb, yb, and zb directions, you need to map, the forces from the body fixed frame of reference into the wheels. So you can do so by this following wheel configuration matrix. We call them as capital gamma, right? And the way to derive this is actually very pretty straightforward. You only are required to consider the force equilibrium in x-axis, y-axis, and moment equilibrium about z-axis. And once you assemble everything in a matrix and vector form, you will be able to, obtain this vector or this matrix gamma. And for a differential wheel robot, gamma matrix would look something like this. And for a omni wheel robot, the gamma would look something like this, right? Where this phi 1, phi 2, phi 3 are nothing but the angle this force makes with the x-axis. So phi 1 would be 90 degrees, phi 2 would be 210 degrees, and phi 3 would be 330 degrees. And yeah, similar case for this tricycle-like robot, right? Where the front wheel is actually powered as well as it's also steerable, right? And that steering angle is given by this variable called theta 1, right? And that wheel configuration matrix would look something like this. So here it is actually a vector. It's not even a matrix. It's just a vector. Because the only term involved here is only F1, because there is only a single wheel that is powering and steering that entire robot. And similar for a mechanical wheel robot, you can actually consider the force equilibrium in x direction, y direction, and z direction, so that you can derive this wheel configuration matrix called gamma, right? Yeah, and another typical question is, if you are given an inertial matrix of the robot with respect to the body fixed frame of reference, so d of theta is given as 10, 0, 0.5, 0, 10, 0.1, 0.5, 0.1, and 1. And you're also given that if the vehicle orientation is 60 degrees with respect to the inertial frame, what will be the inertial matrix with respect to the inertial frame? So you are asked to find out d of eta, right? And in the previous one of the previous slides, we have actually seen the expression for d of eta as j d j transpose. So if I write it over here, j multiplied by d multiplied by j transpose, d is already given in the question, right? This is d of theta. It's already given in the question. And the only other thing that you are required to find out is the Jacobian matrix. So from the question, it is actually given that the vehicle is oriented with respect is 60 degrees. So that is all the information that you need to construct that J matrix. So the J matrix would look something like this: cos 60 minus sine 60, 0, sine 60, cos 60, 0, 0, 0, 1. Right? So now we have J matrix, you have D matrix, and J transpose is nothing but the transpose of this matrix. So if you multiply out all these three matrices, you will be able to get the correct answer as option B. Yeah. Now that's about the mechanics part from week 1 all the way to week 3. Now we move on to week 4, which is all about perception. What are the what is meant by perception, and how do we realize perception, and what are the different sensors that we use for perceiving the real world environment. So you know a typical flow chart or a control scheme of a mobile robot can be described by this diagram, right? This is actually a continuous loop so long as the mobile robot is under operation. This loop is actually continuously executed. So like if you begin from the real world environment, the first stage of a mobile robot is to perceive the real world environment, right? So this block, we call it as perception. And the way it actually perceives the real world environment is through its sensors. Whatever external sensors it has, it tries to perceive the environment. And using the readings from the sensors, it tries to extract relevant information, right? From all the raw data the sensors provide, you use some algorithms to extract very relevant information. And once it has perceived its environment, we go for localization, right? So like as I've already said, once the robot perceives its environment, it will basically try to create a map of the environment with lots of features. And once it has created a map of the robot, it tries to localize its position within that map. So I'll call this as robot start position. So it'll localize itself, and once it is self-aware about its own position, then it should also be aware of its final goal position, right? And then using the tools, using some graph construction method and graph search method, it will out of all the paths that is possible, it will fix an optimal path where it can reach from the start position to the goal position, so that aspect is taken care of by this block. This is where the navigation algorithms run. And once an ideal path has been selected, we'll have a motion controller, which will give the appropriate commands or the appropriate commands to the actuators so that the robot can start executing the motion. And for week 4, this is the aspect that we were focusing on, mostly about perception. And the key definition of perception is the process by which people translate sensory impressions into a coherent, unified view of the world around them. So, like as a human being or an organism, uh, we get a lot of kinds of sensory inputs, right? We get a visual feed of the environment. We get an audible feed through our ears. We get tactile feel of the environment through our skin, right? So we basically fuse all these informations, and then once we fuse all the information from all the sensory inputs, we get a coherent, unified view of the environment. How what are each how does each and every obstacle or objects feel like, right? So that's about perception. And there are also a flow chart uh, about all the processes associated with the perception. We probably won't be discussing that in detail because we have covered that in detail in the previous sessions. And then we have actually talked about sensors, because we ultimately rely on sensors to have to perceive the environment. And depending on the type of sensors that we use, we classify them into two different categories. One such classification, you can call it as whether a sensor is a proprioceptive sensor or an exteroceptive sensor. And another classification of sensor is based on whether or not they are an active sensor or a passive sensor. Right. So in case of a proprioceptive sensor, these are sensors that measures values internally to the system. Like for example, if the sensor is measuring something like motor speed, vehicle load, heading of the robot, battery statuses, such type of sensors are called the proprioceptive sensors. And if a sensor is measuring something external to the environment or external to the robot, such as distance to the objects, intensity of light, those sensors can be classified as exteroceptive sensors. And then whether or not sensors utilizes or requires energy from an external source or not, or whether they utilize an energy source from the environment, for their own functioning, they can be further classified as active or passive sensors. Right? And a very broad classification of all different kinds of sensors, whether or not they are passive, proprioceptive or exteroceptive, or whether or not they are active or passive, were all discussed during the lectures. So like a comprehensive classification has been provided for tactile sensors, for wheel motion sensors. Right? We have actually seen different kinds of tactile sensors that we can use, different kinds of wheel motor sensors that can be used, heading sensors. Then we have seen, beacons, ground-based beacons for localization, then range sensors, motion or speed sensors, or vision-based sensors, and, there are various kinds of such sensors, and whether or not they are PC or EC or active or passive, we have also seen that as well. And the typical question that you can expect is, a very brief, very simple numerical question, such as this one. So it talks about a floor cleaning robot that is placed at a position A, and it detects an obstacle at position B. Right? So if we have a floor cleaning robot at position A, and it detects an obstacle at position B with the help of an ultrasonic sensor. So an ultrasonic sensor will have a transmitter, which transmits some sound waves like so, and it also has a receiver. So the incoming reflected rays, will be received by the receiver, on that ultrasonic sensor module. All right. So given values are, the sensor values are as follows. The speed of wave propagation is 340 meters per second. The speed of sound is given as 340 meters per second. And time of flight is 0.04 seconds. Find the distance between A and B in meters. So as you know, distance is nothing but the velocity multiplied by the time of flight. Right? But here, the time of flight basically denotes the distance for which the transmitted rays to go back and get reflected. Right? So, and we only want half of the distance that is covered by the time of flight. Right? Because we only want this one-way distance, but time of flight essentially covers the distance from A to B and then B to A. So the actual distance between A and B is nothing but C multiplied by TF divided by 2. That's 340 multiplied by 0.04 divided by 2, which turns out to be 6.80 meters. So this distance between A and B is nothing but 6.80 meters. Right. So now we move on to summary of week 5. So this is where we, once we have perceived the environment, we have to essentially localize, or the robot will have to localize itself within that map it create. So the topic that we cover is actually mobile robot localization. Uh, and in mobile robot localization, we are mostly concerned with something called a map-based localization. Right. So there are two schemes of interest where a map can be preloaded into a robot, or it can be supplied to a robot. An entire map of the environment can be supplied to a robot, and then the robot can actually perform localization based on that map and the readings from the sensors and encoders. And another aspect where it can localize is something is using this principle called SLAM, which is an abbreviation of simultaneous localization and mapping, where the robot tries to localize itself while simultaneously building its own map. Right. So in SLAM, a map is not preloaded into the robot. It actively creates a map as it is localizing. So that's why we call it as simultaneous localization and mapping. But in map-based localization that we discuss in this course, we preload a map into the robot. So yeah, we have also seen a few the steps involved in localization. So yeah, we basically begin from this step. So we know that based on the desired trajectory, you can always compute. You can always you can always predict the next position based on the kinematic model or based on the mathematical model we have. And based on the mathematical model, the robot should be moving to the next position. And how much the robot has moved can be acquired from the encoder readings, right? Which essentially gives you, how much rotation each of these motors have made. And depending on the control input that the motor supplies into the robot, we can actually estimate, the next update or the next position. Right. So yeah, the robot is actually given a control input. So I'll mark this as a robot. It has been given a control input, U of t, and based on the encoder readings, it should be, it should be at a different state, xt plus 1. So this is actually predicted from the mathematical models, right? But yeah, that should be predicted from the mathematical model. So I'll also draw a map like this. And this was the previous position. I'll call this xt. And if you supply some control input to the robot, you can consider this red blob to be the robot. And if you supply some control input to the robot, the robot should be at here at time xt plus 1 as per the encoder reading. So if this entire thing is actually the map, I can call this the map. So with the map already given, and if this was the earlier position, and if a control input was given, this should be where the robot has to be, according to the map, based on the encoder readings. So we have a predicted position, and we have correlated that with the map reading. And once it has reached this position, xt plus 1 in the map, it then acquires information from the sensors, right? It acquires information from the sensors, and from the sensors, it actually sees whether it is actually in this position or it is in some other position, right? Because we cannot always rely on encoder readings, because encoder readings will only give you how many rotations that motor had made, but it does not give you an actual realization of the distance that the robot moved, right? Because if a wheel was slipping, or if the wheel was not properly in contact with the ground, the motor would still be spinning, but the robot would not be actually moving, right? So there is a probability that the position predicted by the encoders could be different from the actual position of the robot. So the actual position of the robot can only be obtained through the sensors, right? So from the map, the robot has now two information. What it should be seeing, right? What it should be seeing if it moved from xt to xt plus 1, what it should be seeing, right? That it predicts from the encoder readings. And what it is actually seeing, right, is obtained by the sensors. So, the robot will have to match, what it is actually seeing, or what it is supposed to see, right? If it is matching, then it is fine. It does not have to make any corrections. But if there is some offset, if what it is actually seeing is not matching with what it is supposed to see, then some sort of a correction will have to be made. So this goes, as a loop. If there is a correction, it gives some more control input, and then it will try to match its own position. It keeps going on and on and on. So, that is how, you fuse your information from the encoders and your sensors, so that you can essentially be sure of your current location. This is essentially localization. So the main challenges in localization we have seen is, knowing the absolute position is not sufficient, right? Because a GPS is always not going to be reliant, is not going to be providing that sufficient amount of resolution, right? Localization in human scale in relation with the environment is always going to be a challenge, because as human beings, we coordinate our motions in to a very high precision, right? Maybe probably up to millimeter levels, but a GPS won't give you a resolution up to millimeters. That too in indoors, right? It's not very reliable to completely depend on GPS, because it won't provide you that level of resolution. And planning in cognition step requires more than only position as input. You require further more information from all other possible sort of sensors. And there are some other aspects. Perception and motion plays an important role. So sensor noise, sensor aliasing, effector noise, odometric position estimation, all these things could potentially cause some challenges in localization, right? Because sensors are always riddled with noises. They are also affected by some external, characteristics, some external effects. And more often, for measuring one environmental parameter, you would actually require more than one sensors. And then you will have to fuse the information from more than one sensors to get a very good estimate of that parameter. So that is something that we have to deal in sensor aliasing, and that itself is highly challenging because of all the noises and sensitivity of that sensor with other external parameters. And then we have also discussed on some of the error sources, or some of the errors which can be detrimental to the planning of mobile robots. So, like, there are two errors or two error sources that we deal with on a regular basis. The first error source is called deterministic, and the second error source is non-deterministic. And in deterministic error sources, they can be eliminated, completely eliminated by proper calibration of the system, or if you don't find elimination of these errors to be feasible, you can accommodate these errors into the model, and you can actually try and compensate for these errors using some control inputs. So whatever these errors are, they can be completely eliminated, or they can be accommodated into the model. Either ways, it's actually possible. And in case of a non-deterministic errors, they cannot be completely modeled, because their source is uncertain, and uh, possible ways to eliminate them is also not. Some of these errors, it's not really in control of the designer or the robot, so that it can be fully eliminated. Uh, However, they can actually be modeled using some distributions. Even though we cannot accurately model them, we can actually have a very good representation of this non-deterministic errors by representing them using some error distributions. And the major error sources are limited resolution during integration. So like most often, we will deal with the higher order terms. Mostly, from in accelerometers, we actually receive accelerations, right? And we have to integrate them to obtain the velocities and position estimates. And this integration is actually done numerically, and that will basically depend on the step size or the sampling time of the sensors. So yeah, there is always going to be an effect due to the limited resolution during integration. Right? We cannot have continuous sampling. It only samples in discrete types. So that is one major error source, because of the discreteness or discrete sampling. Any features that comes between these two samples will have to be interpolated, or will be completely missed. So like we won't be able to get the exact dynamics between two sampling points, and there is no way to completely eliminate this sampling time. It's always going to be discrete. So that is one major error source. Uh, and another thing is misalignment of wheels, which is a deterministic error source. Right? So if a wheel is misaligned, we can always you know rectify that misalignment, because like at this point of time, we have that measuring facilities, so that the wheels can be mass produced to a very high tolerance. Another issue is unequal wheel diameters. That is also a deterministic error. We can improve our fabrication processes to iron out these issues. Another aspect is variation in contact point of wheels. So that is not really in our control, right? Variation in contact points of a wheel. Like we can only go up to the extent of designing the wheels, but the contact surfaces of the environment, we have no control over it. And as a result, even if we model the robot to be fully uh, uh, to be moving without any sort of slippage in real life and in real cases, there is always going to be some sort of slipping between the wheels and the contact points. So that is some error that we cannot fully eliminate. And another issue is unequal floor contact point. Again, that is also not fully in the control of the designer, right? And we cannot uh, fully eliminate any sort of errors that is arising due to unequal floor contact as well. And then we in week 5 we also discuss about error modeling. So it's based on the principle that if you have an error, if you uh, have an estimate of an error in from the sensor readings, how will it be propagated into the estimation of position coordinates. Right? If there is any error in measuring that uh, measurement, how should it reflect or how should it propagate in measuring the errors in the position coordinates? So that aspect also we actually cover. So we basically cover, or we basically update ourselves with a very brief kinematics of the differential wheel robot for this purpose. And then we also discuss about this error propagation law, which is given by this expression where Cy is nothing but the covariance matrix representing the propagated uncertainties of the output. And that is Cy, and Cx is nothing but the covariance matrix representing the input uncertainties. And Fx is nothing but the Jacobian matrix, which is derived from that kinematic model. And the Fx has also been defined, how to derive this Fx has also been defined in the course. And, this covariance matrix, this error covariance matrix, you can actually model it on your own if based on some distribution, right? Like if you have a very good idea about how these errors are behaving, or no one can really tell how these errors are distributed, but you can have some sort of an estimate uh, through a lot of experiments, through a lot of experiments using these sensors. And once you do sufficient experiments, you will be able to know what sort of distribution you can fit, over the covariance matrix representing the, input uncertainties. And once you have that, once you have these input uncertainties, you can actually determine the output uncertainty, which is the position estimate using this expression. And then once you have all these estimates, these delta are actually the Jacobian matrices, and this is the uncertainty in estimating the position, and this is the uncertainty in that sensors, and the error propagation is actually described by this expression. And you can consider this to be the error uncertainty in the previous position, and this to be the error uncertainty in the current position. And obviously, at the beginning, there won't be any error uncertainty, right? At time t equal to 0, there won't be any uncertainty caused by uncertainty in position, right? Because at the beginning, at the start, we would exactly know the position of, we would exactly know the current position of the robot, because that is where we keep our robot, right? So at the beginning, we won't be having any position uncertainties, but as time grows, because of the contribution of this term over here due to uncertainties from the sensors, this delta p keeps on growing. It keeps on growing and growing and growing. And eventually, this is how it looks like, right? Initially, we won't be having any uncertainties, but as the robot moves, the uncertainties actually grows, right? So the size of this ellipse basically depicts the uncertainties along each of these directions. And as you can see, along the direction of motion, or along the tangential direction of the motion, the uncertainty is actually much lesser than the uncertainty along a direction that is, perpendicular to the direction of motion. Right. So eventually, this uncertainty grows, and the only way to, check or to have, to bring down this uncertainty is to have an external measurement, or to measure the position, or to match the position using some information from the sensors. So at the next instant, if you have a sensor input, your uncertainty can be brought down. significantly less. And then, in the subsequent steps, it keeps on growing and growing. Yeah, and then, we have actually seen two different aspects of localization. I won't be going in detail with that. We have actually discussed in 2 weeks ago. There are actually two different schemes where we uh, uh, two di two different schemes where we employ localization. One is called Markov localization, and and the other one is called Kalman filter localization. And the key distinction between them is that in Markov localization, you have to estimate the probability that the robot is in the current position for each and every point within that uh, map. So the first thing is that you have to discretize a map into discrete amount of points, and using that Markov localization algorithm, you have to compute the probability that the robot is at each and every grid position. So at every time step, you have to recalculate the probability that the robot is in this at each and every current grid position. So that is how this Markov localization works. So as you can see, calculating the probability of this entire grid for each and every iteration, it's actually a bit computationally expensive or computationally, yeah, high ISO, require a lot of computations. But another good element is that it can actually recover from an ambiguous situation, right? So even if the uncertainty is actually growing very high, very large, it can still recover from a very highly ambiguous situation. But in case of a Markov localization, that is not possible, right? If the uncertainty goes out of bound, it cannot recover. It will be lost. Its sense of position is lost forever, unless it resets. However, a Kalman filter does not require an entire discretization of the grid. Right? So in that regard, it's much more computationally efficient than Markov localization. And their key defining principles were discussed in the lectures as well as in the tutorial sessions. And we have also briefly described what SLAM or simultaneous localization and mapping is all about. And one typical question that we can actually see is given a differential drive robot, the initial pose at A is given by 2, 3, and 25 degrees. So I'll depict this as the initial pose for a differential wheel robot. And so these are the wheels. So initial position is given by 2, 3, and 25 degrees. And the robot moves to another point B. Given the distance between the two wheels as 1 unit, so the distance between these two wheels is given as 1 unit. And the right and the left wheel traverses a distance of 3 and 2.5 units respectively. The absolute traverse distance of the robot is given as. So you can use this formula that is actually discussed in the lectures, where the absolute traverse distance delta S is given by delta SR plus delta SL divided by 2, where delta SR is the distance the right wheel traverses, which is given by 3 units, and delta SL is the distance traversed by the left wheel, that is given by 2.5 units, multiplied by 2, this is something but 2.75 units. You can also consider this in a geometrical sense, right? Uh, if you want to know more about how this equation is derived on, so in this case, I'll call this to be the left side, and this to be the right side. And as per the question, the right hand side of the wheel, sorry, the left hand side of the wheel moves by a unit of, I'll, I'll mark it as 2.5 units. And the right hand side of the wheel moves amount by an amount 3 units. So I'll draw a slightly larger arrow, 3 units. Right? And you are asked to find out the absolute traverse distance of the robot, which is mostly it is nothing but a scalar quantity to denote the distance that the center point of the robot would actually move. So if I join these two vectors, right, this is something like a trapezium, right? So this is the center of the left wheel and this is the center of the right wheel. And if you consider this to be the center of the chassis, delta SR would be nothing but the length of this vector, at the midpoint. So this length of this vector is nothing but delta S. And as you can see, this is nothing but a trapezium, right? So the height of or the length of these two parallel sides are given as 2.5 units and 3 units. And delta SR is nothing but the height of this trapezium from its midpoint, from this point, right? So height of a trapezium, if the height of the two parallel sides are given, is nothing but 2.5 plus 3 by 2. This is nothing but the height of the trapezium. So that would essentially give you 2.75 units. Right? Yeah, so that's about it. I think our time is up. And for week 6 and week 7, I would suggest you to refer to that weekly lectures. And if you have any doubts, you can always let me know. Week 6, we actually see some several aspects about methods of graph construction, right? How to actually construct a graph. And once you construct the graph, you uh, use some of the graph search methods to select the optimal path from the start position to the goal position. And on week 7, we discuss design of motion controllers. And here we have actually discussed various motion controllers based on whether or not they are open loop or whether or not they are closed loop. And then we have actually seen kinematic controllers. And we have also seen dynamic controllers. Right? Like we have seen open loop and closed loop examples of kinematic controllers. We have also seen open loop and closed loop examples of dynamic controllers as well. So if you want to see some sample problems, I would suggest you to refer to the weekly tutorial examples on week 6 and week 7. And for week 8, we will have a discussion on the upcoming Tuesday. So until then, thank you for joining. I am closing this meeting as of now. Thank you.